Morning viewers, this is Kasturi Day. As I've told you that I'll be back with the question answers of laws in motion very soon. So today I'm going to that with those questions. Okay, this is the chapter of laws of motion according to ICSE syllabus, class 9. Okay, so before I start, I will request you to please to subscribe my channel. Please to like, press the like button if you are liking the videos. Share with your friends, and also please do comment if you have any doubt regarding this chapter or any other chapter which I have taught, and regarding this chapter also any clarification you require, please do write it in the comment box. Okay. So before I start, I will request you to please to meditate for just 1 minute, and then we will start with the discussion. Okay. So for a meditation, please concentrate on a point of light. Think that light is a source of energy which is falling on you, and it's giving you lots of energy. The whole body of yours becoming energized, becoming powerful, and you're becoming happy, feeling interest in what you're doing. At last, you are becoming life is becoming successful, day is becoming successful. Happening all because of feelings, supreme power which is helping you is getting also the blessings. So this always making taking all these things and so first question is explain giving two examples each of contact forces and non-contact forces. What are contact forces? Contact forces are those forces that act upon bodies when they are in physical contact. When two bodies are in physically in contact, that is when they are touching these two. You see, this is a body, this is another body. If you keep these two in contact, the forces which they experience, which they act upon one another, is those forces are called contact forces. For example, forces exerted on two bodies while the process in the process of collision or frictional forces you can call. That is a contact force. Okay? And non-contact force is those force which happens, which is experienced by the bodies when they are not in when this is a body, this is a body, but these two are not in physically they are not in contact, but they experience a force. One is experiencing a force from this one, and this is experiencing a force from this one. So that is known as non-contact. Example is electrostatic force or gravitational force. Okay. You must have seen that the uh, apple, which is hanging from a tree, if it the attachment of the apple to the branch that holds the apple that breaks, then what happens? It just falls to the ground. Why? Because of the gravitational force. It will not go up, it will not go sideways, but it will fall to the ground. Okay, because gravitational force is from the ground. It is the earth is pulling the apple towards itself. Okay, so that due to this gravitational force, it is attracted, it's being attracted towards the ground. And also, apple is also creating a force to, it is also pulling the earth towards itself, but that force is much minimal in comparison to the gravitational force. So that's why the earth will pull the apple towards itself. Now, next question is question number 2A. A ball is hanging by a string, okay, from a ceiling of the roof Draw a neat labeled diagram showing the forces acting on the ball and the string. A spring is compressed against, second question B, a spring is compressed against a rigid wall. Draw a neat and labeled diagram showing the forces acting on the spring. And third question is a wooden block is placed on the tabletop. Name the forces acting on the block and draw a neat and labeled diagram to show the point of application and direction of this forces. So first question, that is ball is hanging from by a string by the it is hanged by a string from the ceiling of the roof. So we need to draw the diagram. So if this is the roof from which the ball is being hanged, okay, so there will be two forces acting upon the ball. One is that the weight of the ball is acting downwards. So that is the force which is acting downwards, the weight of the ball which is acting downwards. And there is a tension of the string. Okay, that string is pulling the ball upwards. So the string is pulling the ball upwards, that is moving upwards. The ball is moving upwards, and the weight is pulling the ball downwards. So two forces are opposite to each other. They are acting on the ball. Okay. Next. So this has been just represented by this diagram. Next is the spring is compressed against a rigid wall. Okay. So how to draw the diagram like that? So this, if this fixed portion is a wall, oh, see there is written fixed portion. So let it be this is a wall to which the spring is attached. In the normal condition, the spring is a little bit stretched. Stretched. In the normal position, the spring is like this, little bit stretched. But when it is compressed, okay, then the spring is compressed against the wall. Like the spring is this much. Okay. If you press the spring like this, so it will move towards the wall. Okay. So the uh, force will be like this. It will be a push force which is acting on the spring, making the spring compressed. And there is another force acting on the spring, that is restoring force, that will uh, keep the, that will uh, help the spring to restore its original position. So that is known as restoring force. So one force is pushing the spring towards the wall. Another force is pushing the spring towards the away from the wall. That is restoring force, making it come back to its original position. Okay. Next is another third thing is that a wooden block is placed on the tabletop. Name the forces acting on the block and draw a neat and labeled diagram to show the point of application direction. So see, this is the tabletop. Okay, so you can find the tabletop here, table, and a book is kept on it. Okay. Now, one force, that is the weight of the book. Okay. So that book or block, you can say, so that will act downwards. Okay, acting downwards. And another force will be the reacting force on the block from the table, which is equal to that of the block, weight of the block, which is acting upwards. So one force is acting downwards, weight of the block, which is acting downwards on the table. And another force is which is equal to that of the force of the weight, equal to that of the weight of the block, that will act upwards, which will keep the book in position. Okay. That is known as the reaction force. Now state the effects of the force applied in a non-rigid and a rigid body. How does the effect of the force differ in the two cases? Now, when a force is applied on a non-rigid body, okay, non-rigid, that is, it's a flexible body. It can change its, as it is flexible, so it can change its shape or dimension, and it can also produce its acceleration. That is, it can move the body. It is flexible, no? So you can change the shape, the dimension. You can produce acceleration in it like that. That this change of shape or this dimension, okay, is brought about by changing the intercellular spaces, which are intermolecular places that is, which are present in the particles. Okay. So, but when this forces is applied in the rigid body, because they're particular places, intermolecular places, they are very, not so close to each other. Particles are not so close to each other of this block or this rigid body, non-rigid body. They are not close to each other. That's why they are flexible. So you can move it, or you can change the shape of the dimension. But when we come to a rigid body, their interparticular spaces, they are very less. Okay, so they are rigid. You cannot change in any, if you are applying force on it, but you cannot change its shape or dimension, or even if it is very rigid or very big, then you cannot move the particle, you move the block itself, the body itself. Okay. So it tends to produce acceleration in the body only, but does not change its shape. But you can, uh, if you apply a greater force, you may not change its shape or dimension, but you may change its acceleration. You can produce acceleration in it by applying a greater force. Okay? Interspacing between its constant particles does not change. That's why they are rigid body. But you can produce acceleration in it. In the first phase, you can produce acceleration, you can change its shape and dimension. But in the second case, that is in case of rigid body, you cannot change its shape or dimension, but you can produce acceleration in it. So this is the difference between a non-rigid and a rigid body. Now, what is Galileo's law of inertia? It is stated as Galileo's law of inertia states that an object, if once set in motion, if, if an object is set in motion, it moves with uniform velocity if until no force acts on it. Until and unless a force is applied on it, then you cannot stop that body or you cannot change its velocity. Okay, so if an object once set in motion gets into motion, okay, you cannot stop that, you cannot change its velocity unless and otherwise a force is applied in it. So this is law of inertia, which is stated by Galileo. Okay. Excuse me. State and explain the law of inertia or Newton's first law of motion. Okay. So according to Newton's first law of motion, if a body is in a state of rest or in a state of more, okay, first we come to rest. If a body is in a state of rest, then it will be in the state of rest unless and otherwise a force is applied on it. And if they are remain in the state of motion, they will remain in the state of motion unless and otherwise in the same direction. It will move in the same speed unless and otherwise an external force is applied. So how do you explain that? Let us see. Okay. So explanation will be like that. That if you start moving, okay, if a car is moving, with an example, we can say that if a car is moving, then unless and otherwise you apply brakes on it, okay, unless and otherwise you apply a brake on it, you apply the brakes on it, it will start moving, it will remain to be moving in the same velocity, in the same direction. Okay, in the same direction, the same speed will start moving. It will keep moving. Okay, and when you apply the brakes is nothing but the forces which is applied to it to stop or to reduce its velocity or to change its direction. Forces applied. So unless this force is applied, it will remain in that state of motion in the same direction, the same velocity will move. And when a body, like say the same example, if the car is at rest, it is staying in the garage, unless you switch on the car, that is, a force is applied on the car, you press the accelerator, then I mean, it will not start moving. It will remain in that state. So this is the explanation of this law of inertia. Next is give qualitative definition of force on the basis of Newton's first law of motion. So this definition states, this qualitative definition states that force is that external cause which can move a stationary object or which can change the state of motion of a moving object. It can move a stationary object or it can change the state of motion of a moving object. Now next is more the mass, more difficult is to move the body from rest. Okay. So how much it is true? Explain the statement by giving an example. See, when the mass is more, when the body is heavy, okay, mass of the body is directly related to inertia. Mass of the body is directly related to inertia. That is, it is directly proportional to inertia. Inertia increases with the mass. If mass increases, inertia will be more. If the mass decreases, inertia will be less. Now, what is that? The more the mass of the object, the more will be its inertia. This is understood from an example is that to move an unloaded trolley, we are moving an unloaded trolley. The trolley is not loaded. A small force is required to move that trolley. But when the trolley is fully loaded, it is heavier. So the mass of the trolley increases, so large force is applied to move that trolley. So what happens? Inertia of rest here is more in case the mass of the body is more. Inertia of rest is lower in case the mass is less. Clear? Next. Give reasons. A person falls when he jumps out from a moving train. Why? A coin placed on a card drops into the tumbler when the card is rapidly flicked with the finger. A ball thrown vertically upwards in a moving train comes back to the thrower's hand. The first question, a person falls when he jumps out from a moving train. See, when the person was in a moving train, his whole body was in the state of motion. Especially the lower part of the body, it was in the state of motion when he was in the moving train. Now, as soon as he comes out of the train on the platform is in the state of rest. His feet touches the platform. That time what happens? The lower part of the body comes suddenly to rest position. But his upper part of the body is still in motion. So there is a chance of the person to fall. Okay. When he jumps out of the train from a moving train. Okay. Now, next is when a coin placed on the card drops into the tumbler, when a card is rapidly flipped with the finger. So what happens? You keep a glass. Okay. See, this is the glass. This is the glass. You keep a card on it. You keep a coin here. So if it is a card, say, for example, this is a card and you keep a coin on it. So what will happen? If you flip that card, the card will move, but the coin will drop into the this one glass wire. So what happens? When you're flicking the card, it comes in the state of motion. Previously, the card and the coin both were in the state of rest. Now when we are flicking the card, what happens? The card comes in the state of motion. So it flies away. But the coin on the card, that was still in the state of rest. So what happens? It remains in that state of rest. Now, as the coin has a pull, experiences a pull, gravitational pull downwards. So it will come down into the class. Okay? So it will fall into the class due to the force of gravity. Okay? Next, a ball thrown vertically upwards. Ball is thrown vertically upwards like this. Okay? Now, in a moving train, but it comes back to the thrower's hand. How it is possible? Now, when the ball is thrown vertically upwards in a moving train, the person with the, the ball with the train with the person all in a state of motion with the same velocity as that of the train. Now, due to the inertia of motion, what happens during the time the ball remains in air? Okay, the train with the person inside moves ahead by the same distance. Okay. So what happens to the inertia of motion when the ball was in the train? It will get the time to remain in the air, but it is in the state of motion because it has been moved upward and the air is also moving. So the ball will also be in a state of motion. Okay. Now the person who is sitting in the train, moving train, he will also be in a state of motion with the same velocity as that of the train. This makes the ball fall into the hand of the person who has thrown it. Clear? Am I clear now? Okay. Next is explain the following again. When a train suddenly moves forward, the passenger standing in the compartment tends to fall backward. Why it happens? Because see, when suddenly the train starts, previously the train was in state of rest. The person who is sitting in that train, that person is also in the state of rest. Now the train starts, suddenly it moves forward. So the lower part of the person who is sitting in the train, which is in contact with the train, the lower part of the passenger is in contact with the train. So that part starts in motion, comes in motion. But the upper part is still at rest. So that's why what happens as soon as the train starts, he will have the tendency to fall backward. Here. Now, when a corridor train suddenly starts, the sliding doors of the same compartment will open. When a corridor train starts, what happens? The frame of the doors, frame of the sliding doors, that comes in motion. That comes in motion. But what happens? The door remain in its position of rest. Due to the inertia of rest, the doors remain in the state of rest. Because it was in the state of rest before. So the frame which is in contact with the train, that comes in the motion, but the doors, they are a little bit away from the train. I mean, away from this uh, contact of the train. So that will remain in that state of rest. Okay. So what happens? So the train moves ahead with the train. The train starts, the frame also moves with the state of the train, while the doors slide opposite to the direction of the motion. That is, it remains clear. Next is this. And people often shake the branches of a tree for getting down its fruits. When a person shakes the trees, we see the fruits, they fall on the ground. Right? When you are shaking the tree, the branches of the tree comes in motion. But the fruits, they are still in the state of rest. So when the branches of the trees come in motion, the Fruits which are in contact with the trees, that connection breaks, branches breaks, and the fruits fall on the ground due to the gravitational pull. Now, after alighting from a moving bus, one has to run for some distance in the direction of the bus in order to avoid falling. So, what happens when a person is coming down from the moving bus? He will have to run for some distance, and otherwise he will fall. Why so? Because when he was in a moving bus, his whole body was in motion, state of motion, due to the inertia of motion. But when he alights from the moving bus, the road is in the state of rest, but the bus is in moving state. When he comes down from the bus, when he alights from the bus, and his feet comes in contact with the road, with the still road. So that portion of his body will come suddenly in the state of rest. But his upper part, the other parts of his body, will be in the state of motion still. So what happens? If he stops suddenly, the his lower part will become rest, but his upper part will be still in motion, and that's why he will have the tendency to move forward. That's why he may come down, he will fall down forward. Okay, his upper part will have a tendency to move forward. No? Is that why? That's why he may fall forward. But if he starts running for a some distance, then whole body will have that motion state. Slowly, he will reduce the speed and ultimately stop. Then his whole body will come to rest. So that's why to avoid this falling, if a person alights from a moving bus, he has to run for some distance. Now, dust particles are removed from a carpet by beating it. Why? Because when you are beating the carpet with a stick, with that stick, motion of the stick, the carpet will fly. Okay. But the dust particles, that is the carpet, will come in the state of motion, with the inertia of motion. But the dust particles are still in the state of rest. So they will stay there. They will stay there. But they will come down due to the gravitational force. Gravity, they will fall down and thus separated from the carpet. It is advantageous to run before taking a long jump. When you are taking a long jump, it is easier to take a person if he takes a run before taking a long jump. That becomes advantageous. That is helpful for the person who is taking the long jump because the whole body will come in a state of motion before he takes the jump, and then he will be easily jumping the he will easily take a long jump. But if he suddenly jumps, then he will not be able to take that leap. These are the explanations. See, this is one is A, this one is B. This one is C. This one is D. Carpet. This one is the long jump case. Next, we come to name the two factors on which the force needed to stop a moving body in a given time depends, or one on its mass and velocity. So, two factors on which the force needs to stop a moving body is its mass and velocity. Okay. Two balls A and B of masses m and 2m. One A has a mass m and B has a mass 2m, are in motion with the velocities 2v and v respectively. Compare their inertia, their momentum, the force needed to stop them in the same time. Okay. So first is comparing the inertia of the two new bodies. Can be the inertia of body A is mass, that is m. It is dependent on the mass and velocity. So first we come to inertia of body A is m. Inertia of the body m, body P is 2m. So the mass will be m1 is to 2. Then comparing the momentum, momentum will be mass into velocity. So mass of A we know m and velocity is 2v, so that will be 2mv. And the momentum will be 2mv. And momentum of body B, as it has a mass of 2m and velocity is only v, therefore its momentum will be 2mv away. So therefore their ratio will be 1:1. Clear? Now comparing the force needed to stop both the bodies at the same time. Rate of change of momentum is directly proportional to the force applied on a body as per Newton's second law. Therefore, the force required to stop A, as we know, the momentum for A is 1 and 2mv and 2mv in both the cases, A and B. So that is directly proportional to force. So force will also be 1:1. Here. Now state the Newton's second law of motion. What information do you get from it? Newton's second law of motion states that the rate of change of momentum of a body is directly proportional to the force applied to it, and the change in momentum takes place in the direction in which the force is applied. So Newton's second law has said that states that the rate of change of momentum of the body, that is directly proportional to the force applied to it. That is how much force will be applied. The rate, the force applied, if it increases, if you apply greater force, the rate of change of momentum will be more. Okay, vice versa. And this change in momentum takes place in the direction of the force applied. In which direction the force is being applied, in that direction only the change of momentum will be. So this law provides the quantitative value of the force. That is, it related the force to the measurable quantities such as acceleration and mass. That is, then this law provides the quantitative value of the force. Okay, according to this law, we know the quantitative value of force. What is the quantitative value? The acceleration and the mass. Okay. If we know the acceleration and the mass, then we can calculate the what? The force. Okay. And to know the acceleration, we need to know the momentum. Okay. The velocity rather. We need to know the velocity. And if we know the acceleration, the mass, and the time in which this changes takes place, then we can know the rate of change of momentum. It depends on acceleration and mass. How does the Newton's second law of motion differ from the first law? Now, Newton's first law of motion states it provides qualitative definition of force, whereas Newton's second law provides quantitative value of force. Okay, first law qualitative, second law quantitative. Then first law says it demonstrates the force as cause of acceleration, whereas second law presents force as product of mass and acceleration. The first law, it says that it is the cause of acceleration, it produces the acceleration. Okay, force is required to start its acceleration, to produce its acceleration. But in case of second law, it says it presents the product of the mass and the acceleration. So it relates force to measurable quantities that is mass and acceleration. That's why it's called quantitative. Okay. Now write the mathematical form of Newton's second law of motion and state condition it in. So according to Newton's second law of motion, we know force is equal to the rate of change of momentum or the acceleration of an object depending upon two variables, that is the net force acting on the object and the mass of the object. The net force which is acting on the object, and the mass of the object. So mathematical representation of this law is F is equal to rate of change of that's change in momentum and change in time divided by change in time. So F is net force which is acting on the body, net delta P, that is change in momentum, and delta T is change in time. Okay, so that means what? This will be this one, delta P or to by delta T. Okay, so delta P means what? Change in momentum. So what do we say? Mv minus Mu by T. So that means M, we make common, we take common, and we get V minus U, that is N into A. V minus U by T is A, so N into A. Okay. Next, what are the conditions? Conditions is, that means force is equal to mass into acceleration. So condition will be the speed of the object doesn't approach the speed of light. Speed of the object doesn't approach the speed of the light, and the mass of the object must be clear. Now next we come to draw the graphs to show the dependence of the acceleration on force for a constant mass and force of the mass for a constant acceleration. The first is acceleration. So this is the graph which is showing the on y-axis we take acceleration and x-axis is force. So the mass will be constant, and that will be a line going through the origin, passing through the origin. Straight line passing through the origin. And in the second case, force on mass for a constant acceleration. In this case, force will be taken in the y-axis and x-axis with the mass, and acceleration will be constant, so that will be a straight line passing through the origin. Now, how does the acceleration produced by a given force depend on the mass of the body? Draw a graph to show. When a force is applied on the two bodies that have different masses, then the acceleration produced by them varies inversely to their individual masses. When a graph for mass against acceleration is traced, a hyperbola is obtained. So what happens? How does the acceleration produced by given force depend on the mass of the body? It is that when a force is applied on two bodies, having different masses, two bodies having different masses, force is applied. Then what happens? Acceleration will be produced by them, which will be varying inversely to their individual masses. That means if the mass is more, the force will be more. If the mass will be less, force will be required to produce the acceleration. Okay, so more mass, more force is required to produce the acceleration. Less mass, yes, less mass, less forces will be required to produce the acceleration. Okay. And reversing, that is, if acceleration, then the acceleration produced by them will be varying inverse. That means the mass more, if the mass is more, acceleration will be produced less. More mass, acceleration will be produced less. But if it has less mass, acceleration will be produced more. It is inversely produced proportional to the individual mass. So the graph will be a hyperbola. This will be the hyperbola. Now, why does a glass vessel break when it falls on a hard floor, but it does not break when it falls on the carpet? Why this? When a glass vessel falls on the hard floor, it suddenly comes to rest. So a great force is experienced by that glass vessel, so it breaks. Okay. But when it falls on the carpet, the time duration in which the vessel comes to rest, that will be more. It will get more time to come to rest. So what happens? The carpet will exert less force on the vessel, and so it will come to rest in more time. So that's what happens. It will not break. The vessel will not break. Now use Newton's second law of motion to explain the following. A cricketer pulls his hands back while catching a fast-moving cricket ball, and an athlete prefers to land on sand instead of hard floor while taking a high jump. What happens? When a cricketer pulls his, when he, I mean, catches a fast-moving ball, he will pull his hand back. Why? Because when he is pulling his hand backwards, he will get more time to catch the ball, which will come to rest in his hand. So he will experience a less force from the ball. But if he catches straight away, then he will get very less time and the ball will come to rest as soon as it falls on the hand. So his hand will experience a more large force. So he may get hurt. Okay? Now, when athlete lands from a height on the hard floor, when when a athlete lands on from a height, so he will land on a soft floor like a sand or a sponge is there like that. Why? Because when he lands on the hard floor, what happens? His feet immediately comes to rest. So that time he will experience a very large force and that may exert pressure on his feet and that can create an injury to his feet. But when he lands on sand for some distance or any soft thing is there when he will land, so that will help him to get more time to to help his feet to get more time to come to rest. So that's why he will get more time to, he will get more, less pressure, less force. He will experience less force. Okay, that's why his feet will not get hurt. To avoid that, he needs to land on sand and not on the hard. And name and state the action and reaction of the following cases. Okay? So fixing a bullet from a gun. So action will be firing the bullet and reaction will be recoiling the gun. So firing the bullet, that will be a force action. You're firing that bullet and the coil will suddenly recoil. So that recoil in the gun. That will be the reaction of the firing the bullet. Now hammering a nail. When you are hammering the nail, you are hitting the nail. So that will be the action. And the nail will also exert an equal and opposite force on the hammer. So that will be the reaction of the nail. Now, a book is lying on the table. When a book is lying on the table, it is exerting a force on the table. Okay, due to its weight. So, due to its gravity, rather. So, due to the gravity, it will exert a force. So, that is an action. But the reaction will be the table will also exert a force on the book. Equal and opposite force. So, that is a reaction. Next is a moving rocket. When a rocket starts moving, the fuel in the rocket that will burn and release the gases. And that will exert a force to lift the rocket up. Okay? So that is the action. And the burned fuel will exert a equal pressure on the rocket, allowing the that is the reaction. Okay, and the fuel which is burning and releases a large amount of force in the direction opposite to the movement of the rocket. It will come out of the rocket. So it will move, it will produce a large amount of force in the movement to the direction opposite to the movement of the rocket, and it will this burnt fuel is coming out, as gases are coming out, that will allow the rocket to move upward. That is the reaction. Now, a person walking on the floor, when he is walking on the floor, he is exerting force on the floor. He is exerting force on the floor like this. He's exerting force on the floor. The floor also will exert an equal and opposite force on the person's feet. That's why he will be able to move forward. A moving train who is colliding with a stationary train. Moving train, when it is colliding with a standing train, with a stationary train, is applying a large amount of force on that train which is standing. Okay, that's why it's colliding. Okay, stationary train due to its large momentum because it is moving, so it has a momentum. So it will hit that stationary train and it will produce a large collision, large force on it, large momentum it will produce. And the stationary train will also exert an equal and opposite force on the moving train, which opposes the motion of the moving train. Opposes the motion. The train will stop also. Now explain the following: the motion of the rocket with the help of Newton's third law. When a shot is fired from a gun, the gun gets recoiled. Okay? Then now first say the motion of the rocket with the help of the Newton's third law. So what happens? According to Newton's third law, there is an equal and opposite reaction to every action we know. So like that, when a rocket moves in space, it pushes the gases outside. That's it applies force on the gases in the backward direction, pushes the gas outside from the rocket. So that is, it's applying force. That is, it is applying an action on the force on the now it is opposite to the movement of the rocket. That is an action. But when these gases are there, it's coming out, that will force the rocket to move upward. Opposite direction it will move forward. That is the reaction. Okay? Now the bullet. When a shot is fired from the gun. When the bullet is fired from the gun, a force is exerted on the bullet. You are forcing the bullet to come out. And equal, that is an action. In turn, the gun will experience an equal and opposite reaction by recoiling. Equal and opposite force will be that. That is the reaction. Now, next is when you step ashore from a stationary boat, it tends to leave the shore. When you are stepping on the boat, when a man is stepping on the boat, he will exert a force on as an action. Stands up, he steps on the boat. So he will produce an action. When he is stepping out of the boat gets inclined, tending to leave the shore. So this force, when he is stepping out of the boat and the shore, out of the boat on the shore, the boat gets inclined, which is this produces a force which is equal and opposite as a reaction. It's equal and opposite to the force which the person was applying when he stepped on the boat. Next is when two spring balances joined at their free ends, they are pulled apart, both show the same way. When two spring balances are joined together at their free ends, they are pulled apart. Both the balances show the same reading. Why? Because this indicates that both the action and the reaction forces are equal and opposite. Here, the pull of either of the two balances is regarded as action, and the pull of the other balance is regarded. One will be action, one pull will be action, another pull will be the reaction. So, same reading will be there. Any of the two. Both sides will be applicable. That's why they show the same way. Then to move a boat ahead in water, the boatman has to push the water backward by his oar. A person, okay, by his oar. How does it happen like this? Why does it happen? To move a boat, the boatman will push this way. He will push his oar in the water like backwards. By pushing the water backwards, it is an action. He is pushing the oar, with his oar, he will apply a force on the water to move backward. Okay, that is an action. An equal and opposite force will be acted on the water. The water will exert an equal and opposite force in the forward direction. On the boat, it will act in the forward direction. Then water will exert a forward direction. Exert a force forward. I'm sorry. the water will exert an equal and opposite force on the boat, which will move the boat in the forward direction. Okay. So he will push the water backward. That is the force which is applying on the water, and water will exert an equal and opposite force on the boat to move it forward. Clear now? Next. Next one is this. A person pushing a wall hard is liable to fall back. Now, when a person is applying force on the wall, wall will apply the same amount of force on the opposite force on the person. The wall is big compared to that person, so he will have the tendency to fall back. When a light ball is falling on the ground, when a light ball falls on the ground, it will have, after striking the ground, it will rise upward. But what happens? When a ball falls, light ball, when we strike it on the ground, it exerts a force on the ground, and the ground will also exert a same equal force, same opposite force rather, on the ball, which will move the ball upwards. Okay? Now comment on the statement, the sum of the action and reaction of a body is zero. The statement is wrong. Sum of action and reaction on a body is zero. That is wrong, because Newton's third law states there is an equal and opposite reaction for every action. This is always considered an interaction between two bodies, not a single body. That's why this statement is clear. How does the gravitational force of attraction between two masses depend on the distance between them? The gravitational force of attraction between two masses is inversely proportional to the square of the distance between them. Here, it is inversely proportional to the square of the distance between them. Now, what is the importance of law of gravitation? The gravitation force of attraction is significant to explain the motion of heavenly bodies. So what is the importance of gravitation? It is significant to explain the motion of the heavenly bodies. With this law of gravitation, the heavenly bodies move. That is the motion of the planets around the sun, the motion of the moon around the earth. So these heavenly bodies, they revolve in the space. So that is possible, as we can explain this motion with the help of law of gravitation. It's important. This law is important. So what do you understand by the term force due to gravity? The force with which the earth attracts a body towards itself, rather towards its center, is known as the force due to gravity. Earth attracts a body towards its center of the earth. So that is known as force due to. Next is, a body is thrown vertically upwards with an initial velocity of u. Write an expression for the maximum height attained by the body. So it is moving upward. That means it is going against the gravity. So the formula will be used here will be v square is equal to u square minus 2gh. V square it will be, not v, v square is equal to u square minus 2gh. Okay. So as it is moving upward with an initial velocity of u, but it will come to rest as it moves upward. So v becomes 0. Okay. So that means u square minus 2gh will be the next step. Then u square is equal to 2h, it will be. So h maximum height it attained will be h max will be u square by 2g. A body falls freely under gravity from rest and reaches the ground in time t. Write an expression for the height fallen by the body. The initial velocity, it comes to rest as it is told, or rather, from rest it is starting. Body freely under gravity, it falls from rest. So its initial velocity is u. sorry, 0, rest as it is, so it is, u will be 0, time taken will be t. Okay, so acceleration due to gravity is g, small g. So the height fallen, it will be h is equal to ut plus, because it is coming down towards the earth. So it will be ut plus half gt square. So u, we know it's a 0. So u into t, that is 0 into t, that will be 0. So h is equal to half gt square. Okay. Next, the value of g at the center of the earth is 0. Okay. So what will be the weight of the body of mass m kg at the center of the earth? We know the value of g at the center of the earth will be 0. So what will be the weight of the body, with the mass of the, rather weight of the body, which is having a mass of m kgs at the center of the earth. When we take the body towards the center of the earth, at the center of the earth, what will be its weight? So the weight, we know W is equal to m into g. And as the mass is m and g becomes 0 at the center of the earth, so m into 0 will be 0. So at the center of the earth, the weight of the body will be 0. Explain the meaning of the following statement: 1 kg is equal to 9.8 Newton. Now the gravitational unit of force is, in MKS system, is kilogram force, or you can say kgf. So 1 kgf will be equal to what? Force due to gravity on a mass of 1 kg. So 1 kgf will be force due to gravity on a mass of 1 kg. So 1 kgf will be equal to force due to gravity on a mass of 1 kg. That means mass of 1 kg into acceleration. Force is mass into acceleration. The mass of 1 kg and acceleration due to gravity. That is g meter per second square. So mass is 1 kg, so acceleration is g meter per second square. So that will be equal to g Newton. Okay. Now G, we know the value of G is 9.8 meter per second, average value. So that's why 1 kgf will be as G Newton. So G can be converted, if we put the value of G there, so 9.8, so that will be equal to 1 kgf will be 9.8. Okay. So this much for today. The text questions I have completed. I will give you the, I will, in my next video will be the numerical section. Okay. So till then, please go through the chapter as well as to go through this question answer videos. If you have any doubt, please to write in the comment box. And if you are liking the videos, press the like button, share with your friends so that they can also benefit from these videos. And also do subscribe and do ring the notification bell, because as soon as a new video is uploaded, you will be notified soon. And also, please do meditate before you start your day. Okay, so don't forget that. Okay, so thank you for joining and have a good day.